Another situation that can arise when we're doing epistasis type experiments is the question of, well, what happens when we have two mutants that have exactly the same phenotype? Now, the first issue, as always, that we need to decide is, are these mutants of different loci, or are they different alleles of the same locus? And the way to solve that problem is to look at what happens when you cross them together. So in this case, if we say that there's wild type in the F1, you can probably guess where this is going. But the surest way to look is to say, are there wild type organisms in the F2? And if there are wild type in the F2, and in this case, let's say that there are wild type are present in the F2, then that indicates that these are alleles of separate loci. So let's make this one the original one that we've been dealing with, the little a. And this one we're going to have to say, maybe let's call it white 2 as a locus. It's a different locus than whatever this one was before. We haven't used C's yet, so I'm going to give this one little c. And the reason why I'm making it a little c is obviously because we see a wild type phenotype in the F1, indicating that both loci are recessive to their corresponding wild type alleles. So I can give this one a big C, and I can provide this one with a big A, as we've done before. That makes the F1 a dihybrid, as we expect. And now the question is, what are we going to see in the F2 when this is selfed or intercrossed, depending on the organism? Now, again, we'll make the assumption that we're dealing with something that is assorting independently or 50 map units apart on the same chromosome, such that they are genetically independent of one another, which would produce the 9:3 to 3:1 ratio that we're so familiar with. The interesting thing here is that the mutant phenotypes, because they're the same and can't be distinguished from one another, what we see is this sort of situation, where the different mutant categories all have the same phenotype. So these would all collectively have a white phenotype. And this one would be wild type or purple. Wild type, i.e. purple, I should say, in this case. But wild type in the genetic or the generic case. So this is a ratio that produces a 9:7. A 9:7 is one of the most difficult ratios to see. There's only two phenotypes in the F2. It's important to note, though, that one of those phenotypes is wild type, which allows you to infer that they are separate loci. If they are separate loci, then this must be a dihybrid. And if this is a dihybrid, and presumably if there's not genetic linkage, then you are seeing a genetic 9:3 to 3:1 ratio present in the F2. This can look, in some cases, if you're not careful, this could appear to you, if you're not cautious, as a 1:1 monohybrid ratio, but that's not the case. The data will be enough, or will have a large enough sample size to convince you that in fact what you are looking at is a 9:7 ratio. The technical term for this particular pattern is something called complementary gene action. And what we mean by that is whatever the A locus and the C locus are doing in their wild type situation, they have the same mutant phenotype. So they contribute towards the same wild type phenotype when their wild type allele is present. So they're complementary to one another, and a loss of either of them gives you the same particular phenotype, in this case the white. So a 9:7 is not really an epistasis type of situation. It's not really fair to call it epistasis because we don't have masking going on. But so we can, cross that out. So here's what you get when you have two recessives that have the same mutant phenotype, and therefore their wild type products are said to be complementary in gene action. This produces that 9:7 ratio. In the next clip, what we'll do is we'll say, well, what happens when we have two mutants that have the same phenotype, where one is recessive to its corresponding wild type allele and the other is dominant to its corresponding wild type allele? And what you'll see in this case is that we don't get a 9:7, but rather now we're going to have other phenotypic categories grouping together, and we'll see how that goes in a minute. Okay, let's tackle the case now where we have two mutants with the same phenotype, but one is a recessive to its corresponding wild type allele and the other is a dominant. We haven't used ease yet, so let's go with ease, say. If I say that the white 3 mutant is mutant because of a dominant letter E, and again, white, as we've seen the original white as a little a, then we would say that the original white line has the wild type allele, which I'll define as a lowercase e with a plus. And then this one here obviously has the wild type allele of the A locus. In this case, things are going to be slightly different. First off, the thing is, we'll see that the phenotype of the F1 will be white as opposed to wild type, which is what we saw in the 9-7 case just prior. The reason here now is that we have a dihybrid in the F1. And the presence of that mutant allele from the one line is enough to give us the white phenotype in the F1. Now, if we take this and self it to make an F2, again, if we work with that assumption of genetically unlinked loci, we get a 9-3 to 3-1 as before. And now as we go through and phenotype these different genotypes, we'll see that the pattern we get is not a 9-7, but rather something else. Okay, starting off with this one here. This one would be phenotypically white because it's got that big E. Here we have wild type at the E locus and also at least one wild type allele at the A locus. So this one would be wild type in phenotype. So it would have the purple phenotype. In this case here, we're little a, and we have the big E. So this one's the double mutant category. They have the same phenotype, so this would be white as well. Okay. And in this case, we're wild type for the E locus, but we're also homozygous recessive mutant for the A locus, so this would also have the white. So in the end, what we have is, again, only 2 phenotypes. We have mutant and we have wild type. Again, can't emphasize this enough. The presence of the wild type in the F2 allows you to determine that these must be alleles of separate loci. If they were alleles of the same locus, you would never have recombination that would produce a wild type genotype that has a wild type phenotype. Okay, so we have 3 that are wild type in the 9-3 to 3-1, and the other ones grouped together and are white, and that adds up to 13, as you'll see. So 9 plus 1 is 10, and the 3 gives us 13. So a 13-3 wild type to mutant, or in this case, specifically white, is the ratio that you would expect to see. Now, this is another one that can be tricky to spot sometimes because a 13-3 is very, very similar to a 3-1. Again, how do you know that you're dealing with a 13-3? Because you take 2 mutant lines, you cross them together, and they show that in the wild that there is wild type in the F2. If there's wild type in the F2, then you know that you're dealing with a dihybrid in the F1. And if you're seeing a ratio that's a modified 9-3 to 3-1 ratio, if you've got these 2 phenotypes, 13 mutant to 3 wild type, then you know that you're dealing with a case where you have 2 mutants that have the same phenotype, where one is a dominant and one is a recessive. Again, this isn't really an epistasis type of situation because it's not really reasonable to talk about one locus masking another locus when there's nothing to mask because they have the same phenotype. But again, because this is a modified 9-3 to 3-1 ratio, they are often discussed at the same time when epistasis type interactions are discussed. So this is one to watch out for, a 13-3. Again, the data will be large enough, the sample size will be large enough to convince you that you are dealing with a 13-3 and not some monohybrid ratio. But the point remains that you know that you're not dealing with a monohybrid ratio because you have wild type in the F2 when you cross the 2 mutant lines together.